So hello everyone. Let's get started by going over the last quiz. So this was quiz number 5, and the first question was about these three transfer functions: G1, G2, and G3. So the question asks you, the first question asks you to find the location of the pole of the closed loop systems made of each of these three transfer functions with a proportional controller. So the type of the closed loop that we're talking about is made of each of these three and a proportional controller. So we have each of these three as our system. So I'm going to call it GI to keep it general. So the output is Y. So we feed back the output with a negative sign and compare it to the reference input. And the error goes to a single gain K, which we call a proportional controller. And this produces the input to the system, and this is the error signal, the difference between R and Y. So the first step is to find the closed loop transfer function with each of these three open loop transfer functions. So let's call the first one G1 closed loop. G1 closed loop would be so what G closed loop means is the ratio of Y over R. So we are trying to simplify the entire feedback loop with a single transfer function. So input is R, the output is Y. So we apply the golden rule here. So what sits between R and Y is K times the transfer function of open loop, which in this case is 1 over 2s plus 1. And in the denominator 1 plus, because it's a negative feedback. And the content of the loop is the same, 1 over 2s plus 1. So this is the transfer function of the closed loop system. We have to simplify it so we can see the poles easier. So the approach is straightforward. We need to make 2s plus 1 the common denominator of the denominator, so we can simplify it with 2s plus 1 from the numerator. So if we did this, we'll have k in the numerator, and we have 2s plus 1 plus k for the denominator. So in order to find the pole of the closed loop system, you set 2s plus 1 plus k equal to 0. So 2s plus 1 plus k equal 0. So the value of the pole of the closed loop system, pole of closed loop would be, so it's 1/2 times minus, so it's 1/2 times minus 1 minus k. So that's the location of the pole of the closed loop system with G1. And you can repeat the same thing with G2 and G3. The only difference is that the transfer function would be replaced by G2 and G3. So we solved the first portion of the quiz. Any questions before we move forward? Okay, and the next step is use MATLAB, and of course you can plot this. So you can, let me show you. You can find where this pole is located by putting it on the complex plane. So if this is your imaginary axis and this is the real axis, so imaginary real. The question is, where is this pole located? And the way to answer this question is by calculating the location of the pole for various values of k, starting from 0 and going to higher numbers. So you can quickly create either a mental or an actual table. So k, sp of closed loop. So when k is 0, value of the closed loop pole is minus 1/2. When k is 1, the value of pole is minus 1. When k, for example, is 3, pole is located at negative 2. And as k goes to larger and larger positive numbers, as the controller gains would assume larger and larger numbers, the pole will go to a farther to the left on the real axis. So at k equals 0, it is located at here at negative 1/2, and it simply goes towards larger negative numbers as k goes to infinity. So that's how the location of the closed loop pole changes. It is real, so it stays on the real axis, and essentially this is the root locus. This is the root locus. So this shows you how the closed loop pole changes its location as k increases in value. Now, the effect of that is, as k goes higher, as k gets larger, this system becomes faster and faster because the pole shifts towards the left of the real axis. We can do the exact same thing using MATLAB. So let me open the online version. So if you go to octaveonline.net, this is the online version, a browser-based version of MATLAB. So what you need to do in order to create root locus, of course, you need to introduce s as this special variable, and then define the transfer function of the open loop. So g1 is 1 over 2 times s plus 1. So that's the transfer function. And then the next step is to simply use the command root locus. So r locus of g1, as we called it. So this essentially calculates the closed loop transfer function, and it looks for the roots of the denominator of the closed loop transfer function. As you can see here on the screen, you have this asterisk that shows when k is equal to 0, the location of the pole is the same as the location of the pole of the open loop, and as k increases, you move farther and farther to the left. Now, for all of these cases, the damping ratio is 1 because the pole doesn't have any imaginary part. So as long as the imaginary part of the pole is equal to 0, we are dealing with the real pole, and the damping ratio is 0. What it increases as you increase value of k is the natural frequency. So the distance to the origin gets larger and larger, so the system gets faster and faster. So, and you can also compare. So you can talk about g2. So g2 was 2 over 2 times s plus 1. And you can define g3 as 3 over also 2 times s plus 1. So we have the three transfer functions. And our locus allows you to put these side by side. So g1, g2, and g3. On one figure, draw the three. So let me make sure we have g1, we have g2, and we have g3. Okay. So apparently this doesn't allow for multiple on the same. So we can look at g2 just by itself. So root locus of g2 you can see again, because the denominator of the open loop transfer function is the same, this root locus is exactly the same. So as you increase k, basically it starts from -1/2 and goes to the left. And the same with G3. So if you look at root locus of G3, the same way. It still starts from -1 and goes further to the left. So the expected change in response is similar for these three transfer functions. So then you may ask, what is the difference between these three? The difference is in the, so let's do a quick calculation for G2, for example. So let me see it. So if you repeat this step of finding the closed loop transfer function for G2, so G2 closed loop would be, which is y over r, would be k times 2 over 2s plus 1, 1 plus k times 2 over 2s plus 1. So 2s plus 1 can become the common denominator again. So this, in the numerator, we'll have 2k. In the denominator, we have 2s plus 1 plus 2k. So the difference, as you compare the denominator of G1 closed loop, so this was G1 closed loop, versus G2 closed loop, you can see that if you find the SP of closed loop, you can see that this becomes 1/2 times -1 minus 2k. So the difference is, for the second system, the speed at which the pole moves to the left is twice as much. So increasing gain by 1 unit has twice the effect of increasing the gain by 1 unit for the first case. So the speed at which the pole moves to the left is more. And it would be even more when you look at G3, because k will be multiplied by 3. So that's the answer to the first two parts. Then in the third part, you're asked, use the final value theorem to find the response of each of these three closed loop systems to a unit step input. So if R is 1, so the question is, if R is 1, what is the value of Y in steady state? So if R is 1, which means R in Laplace domain is 1 over S, the question is, what is Y steady state? So how will the controller perform, or what is the performance in steady state? So let's start from G1 closed loop. So according to final value theorem, Y steady state is equal to S, Y in S domain when S goes to 0. So we have S, then we need to multiply this by R of S, and further multiply it by one of these closed loop transfer functions that will give us Y of S over R of S. That's the transfer function. So let's start with G1. So we have S, R of S is 1 over S for all cases, and G1 closed loop, as you can see from here, is K over, so G1 closed loop is K over 2s plus 1 plus k. So the first two s in the numerator and denominator will cancel each other. So if you let s go to 0, the theorem predicts that Y steady state is going to be equal to k over 1 plus k. That is Y steady state. So if k is 0, obviously Y steady state would be 0. K equals 0, by the way, means we are not controlling the system. So look at the block diagram. If k is 0, if this value is 0, the feedback loop is actually open. So we are not adjusting value of u based on the changes in R at all. So there is no connection. So that's why no input is applied to the system, and y steady state naturally is 0. Now, as k increases, as k goes to larger values, what you can see is that y steady state gets closer and closer to 1. So it gets closer to the ideal value. Remember, the whole purpose of the control loop is to make sure that y gets as close as possible to r and stays as close as possible to r. So when r is 1, we are indicating that we want y to get to 1 and stay equal to 1. So the trend is as k increases, y actually gets closer and closer to 1. Now, it never gets exactly equal to 1 unless you have a very, very large number for k. So this was for G1. If we look at G2, so for G2, we can repeat the same process. So y steady state is S times 1 over S, which is R, times the closed loop transfer function, which in that case is 2k over 2S plus 1 plus 2k. And after simplification, this simply becomes 2k 1 plus 2k. So the same trend. As k goes up, y gets closer to 1, but at the speed at which this gets closer to 1 is more. So with the same value of k, the second transfer function gives you a value that is closer to 1. So that was the third part. So we did plot the root locus, and the expected shape of the unit step response for various values of k. So if you look at the closed loop transfer function, let's again start with G1. This is a first order transfer function, and as it receives an input of 1, which is a unit step, the expected response is that it rises and gets to the final value. So let's draw that for G1. So for G1, so the response to a unit step is that it starts from 0 and gradually increases and levels off. So this value we have calculated is going to be k over 1 plus k for G1. And the effect of k, would be, if you look at the pole of the closed loop, is as k increases, the pole of the closed loop moves farther to the left. So if this is for k1, if k increases to a different number, let me switch colors so we can distinguish. So if this is k1, as k increases, the steady state value gets closer to 1. But what is significant is, let me draw this and then I'll move it. What is significant is that the rate at which the system moves becomes faster. So let's see if I achieve this. So this is a faster rate of response. So the fact that this to the left, it shows that it basically gets to the steady state value faster. That's the effect. So as k increases, transient response gets faster. So that's the expected effect. So that was the review of this quiz. Let me go back to the last example that we discussed and also talk a little bit about what we did there. So our interest still is in predicting the response of closed loop systems with proportional controllers. So we started from transfer functions. We talked about how to find the closed loop transfer function and discuss how the response of closed loop systems change when we have a transfer function. For example, here we dealt with a transfer function of a system that was fourth order, and we talked that because it's a fourth order system and the open loop system has 4 poles, the same will remain. The number of poles will still be 4 when we close the loop. And the root locus basically shows how those poles change as k increases from 0 to infinity. So for example, this system, because it has 4 poles, for the root locus has 4 branches. And each of them starts from the open loop poles. So the open loop poles for this system was located at 0, -5, -15, and -20. So each of these branches started from one of these locations. So if you look closely here, if I zoom in, you can see that each of these branches actually started. So this branch, the blue, the darker blue, started from 0, which is associated with the open loop pole at 0. The next one started at -5, which is associated with s plus 5. The third branch started at -15. And this branch, by the way, ends at the 0 of open loop system, which is located at -7. So -15 when k is 0, and as k increases, eventually it gets equal to 7 rather, with the negative sign. So that is a good place to review one of the properties of a root locus, that it has as many branches as the order of the system, and some of those branches will end at zeros of open loop. As many zeros that the open loop system has, as many branches would end at zeros. Otherwise, these branches will go to infinity according to the behavior of the system, according to the polynomial and the way it basically dictates the change in location of the poles. And then we looked at this system. This is a second order system, which means the root locus has 2 branches. So what we did here, we first of all turned this state space model into a transfer function. So we used this formula, GS is equal to C times SI minus A inverse times B plus D, and turn that into a transfer function. So we found the transfer function, which was 1 minus S over S times S plus 3. So it has 2 poles. This is the transfer function. Then we went ahead and closed the system. So this is the transfer function of the open loop system. Without any controller, it has 2 poles at 0 and -3, and 1 0 at +1. Then we went ahead and closed the system with a proportional controller, and we repeated the calculation to find the closed loop transfer function, the ratio of y over r, using our golden rule. So we then found the polynomial for the denominator of the closed loop transfer function, and we found the location of the poles, and we created our little table and showed when k was 0, we had 2 poles, and as k increased, the location of the poles increased. And basically, this is the root locus. So 1 starts at 0 as we expect, and 1 starts at -3. These are the open loop poles, and they come closer to each other as k increases. That these 2 branches, each showing the location of one of the 2 poles, they meet at this place, and then they move on a semicircle. As k increases, they keep changing. The damping ratio keeps decreasing, and eventually at k exactly equal to 3, we have damping ratio of exactly 0. And as k increased further, the 2 poles went to the right-hand side of the complex plane, which meant the system became unstable. And as you keep increasing, one of these branches will go to the 0 of open loop, and the other one simply goes to infinity um, um, also on the real axis. So this entire calculation was based on taking the state space model and turning it to a transfer function. The other approach is just stay as in the state space model and repeat the same process. So there we made a simplifying assumption that we assumed R was equal to 0 and found the closed loop A matrix. The closed loop A matrix is A of open loop minus B of open loop times K times C, where K is the controller gain, it is the proportional gain. So we applied this formula to our system and found A of closed loop, and as you expect, A of closed loop is a function of K. So when you find A of closed loop, which is this, K would be very much present. So then we went ahead and found the eigenvalues of the closed loop, and we showed that they're identical. So the polynomial for eigenvalues of closed loop system was identical to polynomial of the denominator of the transfer function of closed loop. And if you plot the root locus, you get the exact same image and same information. So let's now continue with this example. So I'll give you a few minutes, a couple of minutes. So we want to start from the two differential equations, obviously, and find first of all, find the transfer function between H2, which is the level of this second tank. So this is H2, this is H1. So we want to find a transfer function for the open loop between U, so this is U of t, it's the flow that comes to the system. So we want a transfer function between H2 and U. And please assume that the cross-section area of this tank is A1, C1 defines this orifice, A2 is cross-section here, and C2 defines the flow rate through the second orifice. So the first thing is to find the open loop transfer function. Please go ahead and find that. And then we need to find the closed loop transfer function with a proportional controller. So if you look at each of these two tanks and write the conservation of volume. A1 H1 dot is change of volume in the first tank. That is equal to volumetric flow coming in minus volumetric flow going out. So U minus C1 H1. And for the second tank, A2 H2 dot is C1 H1, which is the input to the second tank, minus C2 H2, which is the output, the flow going out of the second tank. Now, if you're interested in writing the transfer function, we need to take each of these two differential equations and turn them into an equivalent Laplace domain equation, algebraic equation, to get rid of the derivatives. So from the first one, we get A1S plus C1 times H1S is equal to U of S. That's from the first equation. And from the second equation, we get A2S plus C2 times H2 of S is equal to C1 H1 of S. So in the first equation, we have a relationship between H1 as output and U as input. In the second equation, we have a relationship between H1 as input and H2 as output. And our transfer function is a relationship between input U and H2 as output. So we have to combine these two equations algebraically, which is now easier to do. There is no differentiation, to get rid of H1 between the two equations. So that's the step that we need to take. So if we rewrite the second equation, so it would be A2S plus C2 times H2 of S is equal to C1. So for H1, we are going to substitute from the top equation. From the top equation, H1 is equal to U of S divided by A1S plus C1. So from here, you can see that A1S plus C1 times A2S plus C2 multiplied by H2 of S is equal to C1 times U of S. So we are now ready to form the transfer function. Please let me know if I missed a step. So H2S over U of S, output over input, therefore would be C1 over A1S plus C1 times A2S plus C2. So as we expect, this is a second order system. There are two poles for the transfer function. So there are two open loop poles. So let's find those. So S1 open loop is equal to, what is the first pole? What value of S will make the denominator go to 0? What is the first one? So what value will make the denominator go to 0 for the open loop? The first one is minus C1 over A1. So minus C1 over A1 will make the first pair of the first parenthesis go to 0. So therefore, the second pole of open loop is simply minus C2 over A2. So there are two poles for the open loop. So the question is, if we put this system into a proportional controller, so if we put H2S over US here, which will give us the output Y, which is the same as H2, and take this H2 and compare it with the desired value of H2, which we call R, reference input, through this summation, and then multiply the difference between the two by a constant number to calculate how much flow we let come to the first tank. This is the proportional controller. So essentially, if you want to implement this proportional controller, what you would have is a sensor here to monitor the level of the second tank. So you put a sensor here. So you stick a sensor here. And this sensor will give you H2. So then you take this signal and compare it to a desired number. This could be a constant number or a time varying number. But you say, I want the level of the second tank to be at this height, 5 feet, 10 meters, 2 inches, whatever that number is. So you continuously compare this number that comes from your sensor with the desired number, and that creates an error. And you take that error and multiply it with a number, a constant number. So let me show you. So this, you take this H, and from here you bring R. This comes with a negative number. So this gets multiplied by a constant number K, and this in turn adjusts this valve. So the difference between R and H2 it gets multiplied by value of K, and literally you open and close the valve based on that number. So the larger the value of K, the more turn you would turn your valve in response to the same value of error. So larger gains means more flow in response to the same value of error. So that's the meaning of a larger K. And that's a good place to discuss that simply increasing K is not a numerical exercise. Let's say your K is 1. That means for every unit of error you have, you need to allow for 1 unit of flow to come into the tank. Now if your K becomes 100, if your K becomes 100, you need to have a valve that is 100 times larger so it can allow 100 times more flow coming to the tank. Do you see the difference? So it's not simply a number that you increase the controller gain and everything is just fine, it's just a number. It has real life, real world implications. So if you increase controller gain, most of the time it means higher cost of implementation. So K essentially is not free, increasing K. So it has, there is a cost associated with it. Okay, so let's keep working. So I'll give you 30 seconds to find Y over R. What is the closed loop transfer function? Find it, please. And once you have it, then find the location of poles of the closed loop. And we want to discuss how K affects those poles. Okay, so how do you solve this? In the numerator, you have what sits between input and output, which is k, and this transfer function. And let's give it a name so it's easier to deal with it. So let's simply call it g. So it would be k times g in the numerator, and in the denominator it's 1 plus the content of the loop, which is k and g, so it's k times g. So let's go ahead and substitute. So it's k times this long transfer function, which is c1 over a1s plus c1 multiplied by a2s plus c2. This is the numerator, and then 1 plus the same thing, k times c1 a1s plus c1 times a2s plus c2. Make sense? Any questions so far? So we need to again simplify, and the way to simplify is to eliminate the numerator in the denominator in the numerator. So we'll make this the common denominator down here so we can simplify it. So after simplification, what is left in the numerator is k, the controller gain, times c1. And in the denominator, we'll have a1s plus c1 times a2s plus c2 plus k times c1. So that's the transfer function that we're after. This is the closed loop transfer function. That's the ratio of y over r. Let's call it h. Now, before going any further, let's give this, let's assume a few numbers. So what do I mean? I mean, let's give C1 and C2 and A1 and A2 some numbers so we can compare. So let's make this assumption that A1 is equal to A2, and they're both equal to 1 meter squared. So the surface of these two tanks are identical. So we are dealing with identical cylinders. But to distinguish between the two tanks, let's assume C1 is 5 and C2 is 1. With proper unit, which the unit of C is meter cubed over second over meter. So it's meter squared over second. So that's proper unit for C. So when it's multiplied by H, it would be a unit of volumetric flow, which is meter cubed over second. Okay, so with these two numbers, now let's look at these two poles. The first pole, we are dealing with open loop so far. We haven't discussed the closed loop pole. So open loop poles, we have S1 of open loop located at negative C1 over A1, which would be at negative 5. And the second pole, also for open loop, is located at negative 1. So we have two real poles, one located at negative 1 and the second one located at negative 5. So if you put this on the complex plane, so real, imaginary, one of them is located here and the other one is located here. So negative 1, negative 5. Okay, where did negative 5 come from? It came from minus C1 over A1, and this came from minus C2 over A2. So which one of these two poles would you call the dominant pole? Negative 1 is dominant, which means its effect is going to last longer. So as you turn on the valve at the top, the pole associated with negative 5, its effect would quickly diminish. But the effects of the second pole, which is located at negative 1, would dominate the response for a longer time. But why is that? What does it mean physically that the first pole is not dominant, but the second pole is dominant? If you look closely, you can see that this negative 5 comes from the fact that C1 is 5 times larger than C2. And if you look at the physical system, C1 defines how much fluid loss we have from the first tank, and C2 defines how much fluid loss we have from the second tank. Now, the fact that this is very large, it means that the steady state level of the first tank would be reached much quicker than the steady state level of the second tank. So it will reach its steady state value much faster than the second tank would reach its steady state value. So that's the reason. And we can use Simulink actually to look at this. So why don't you open Simulink? And with these numerical numbers, create the transfer function for each of these two subsystems. And I want you to see that if you give it, now it's all in open loop. We are not doing any control. So if you give a unit step for U as the input to the first tank, the level of the first tank would reach steady state much faster than the second tank would reach. So the approach is, again, I realize that people watching this online would not see my screen here. But what I'm doing here for their benefit is I opened MATLAB and I opened Simulink, the browser. And after Simulink browser is open, we'll create a new model in Simulink, and then we'll drag one transfer function for each of these two tanks. So go ahead and do it as a practice before I show you how to do it. So if you have your Simulink open, drag one transfer function for each of these two tanks. And these two transfer functions should be connected because the output of the first tank enters as input to the second tank. So they should be connected. So again, for the benefit of folks who are watching the video, what we will create in Simulink will look like this. So in Simulink, we will create one block one block that shows the behavior of the first tank, and the behavior of the first tank essentially is this. So if U enters this, what comes out of this first block is H1. So what comes out of the first block is H1, and this enters the second block, and what comes out of the second block is H2. So what needs to go in the first block? Look at what we found in the equation 1. So in the first block, it is the ratio of U as input, H1 as output. So it is 1 over A1S plus C1. So what goes in here is 1 So what goes in here is 1 over A1S plus C1. That is the transfer function between U and H1. And what goes in the second block is the transfer function between H1 as input and H2 as output. H1 input as H2 as output. If you look at the second equation here, you can see that H2 as output, H1 as input, it requires a transfer function that has C1 in the numerator, and in the denominator we have A2S plus C2. So what goes here, and we will recreate this in Simulink. So it's C1 over A2S plus C2. So go ahead, please, and create this in Simulink and give it a unit step input. So unit step input means U of t is 1. So we can look at how H1 changes with time and how H2 changes with time. So we are going to attach a scope to each of H1 and H2 lines so we can compare. So let's go ahead to continuous. So we will, of course, we need to create a new model. So click on this icon and create a new blank model. And then add this transfer function here. This would represent the first tank, and add the second tank and connect the two. Now, by now we know the content of the line connecting these two blocks is going to be H1. And the content of this line is U. So we go under sources, grab a constant, because we are going to simulate the step response. So we are going to connect this constant to our first tank. So this is our U. What comes out of this one is H1, and what comes out of here is H2. So we want to look at them side by side. So what I'm going to look at is a mux. So I can bring both of H1 and H2 to the same plot as we did before. So yes. Oh, absolutely. I apologize. So better? Okay. So I dragged, let me repeat what I did. I went under continuous. I dragged a transfer function from continuous here and dragged it again for the second tank. So this is tank 1, which is the relationship between U and H1. And this is tank 2, which is the relationship between H1 and H2. And I said, because we want to bring both H1 and H2 to the same plot, I'm going to bring a mux connector. So I'm going to connect this here and connect H1 also. And then the output of this mux, which contains both H1 and H2, will go to a scope. So I'm bringing a scope and connecting it here. So the first block diagram is 1 over A1S plus C1. So it is, what was A1? A1 was 1, right? So it's A1S plus C1, and C1 is 5. So it's going to be 1 and 5, that polynomial of the denominator. So it's 1 over S plus 5. The second transfer function has C1 in the numerator, which is 5. And in the denominator, we have A2, which is 1S plus C2, which is also 1. So it's 5 over S plus 1. So that's the second transfer function. Let me know if you have any questions before we go any further. So for people who are watching online, I created a mux block here. So it's 2 inputs going to 1 output. So this basically went to a scope. And it was attached to H2 as well as H1, so we can compare H1 and H2 at the same time. So that's what we are creating in Simulink. So if you're ready, click on Run, and then look at your scope. So the expectation is that the level of both tanks would increase. The level of both tanks would increase. But one of the two tanks, which is the first tank, by the way, is much faster. Look at this. The blue reaches its steady state in less than a second. The yellow, however, keeps changing instead in transient for about 5 seconds. Can you see that? So that's why we call the pole that creates this response, the yellow response, the dominant response, everybody. Because the effect of blue quickly disappears in about 1 second. But the effect of yellow stays around much longer. So for people who are watching the video, if you look at the plot, this level, so if you give it with the numbers that we assumed, the simulation shows that this goes up to 2, the 0.2 rather. The steady state is 1/5 or 0.2. So this starts from here and goes to 0.2 quite quickly. So this is 0.2. This is H1. But H2, even though the trend is similar, it takes much longer, 5 times longer, to reach to a steady state value for H2. And that basically shows that and the steady state value for H2 is 1. So it reaches 1. But if this takes 1 second to go through transient, this takes 5 seconds to go to transient. So, and if you look closely, the pole for the first transfer function is at minus C1 over A1. So the pole associated with the first transfer function, this is located at -5. The pole associated with the second transfer function, this is at -1. So this is the dominant, which produces the response that stays around longer, and this is not a dominant response, which produces the response that diminishes quickly. So this is a perfect example to show the meaning and the implication of a dominant pole versus a non-dominant pole. Okay, so let's now pick up from where we left off, which was, so we found, let me switch. So we found the transfer function for the closed loop system, as kc1 in the numerator, and we have a polynomial for the denominator. So let's go ahead and now find the poles of the closed loop system. So where are the poles of the closed loop system located? So as you start controlling, what are you going to do to the two poles? So what we need to do is to set the denominator of the closed loop system equal to 0. So it's A1s plus C1 times A2s plus C2 plus K times C1 equals 0. So if we set this equal to 0, we'll find the poles of the closed loop system. So in order to find the poles, we need to find the polynomial. So let's go ahead and multiply this now. So it would be A1, A2, S squared plus A1, C2 plus A2, C1 quantity times S plus C1, C2. So A1, A2S squared, A1, C2S, A2, C1S, and C1 times C2 plus K times C1 equals 0. So we need to find the two poles. So this is a second order polynomial, so quadratic equation. So S1 and 2 of now closed loop is going to be equal to. So minus b, which is this parenthesis. So minus a1 c2 plus a2 c1 plus minus square root of b squared. So a1 c2 plus a2 c1 squared minus 4 times a times c. So minus 4 times a1 a2 times c1 times c2 plus k plus k, close parentheses, and this continues. And this is all divided by 2a, which is 2 times a1 times a2. Please double check this. So we applied the quadratic equation. So it's a, b, and c, the coefficients of s squared, s, and s to power 0. So minus b is the first term, plus minus b squared, minus 4 times a times c. And for c, I have factored c1 out because c1 is repeated in these two terms. So you can factor c1 out, so it's easier to write it as c2 plus k over 2a1, a2. Okay, and why are we doing this? We are trying to do what? What are we trying to establish? We want to know the location of poles of the closed loop system. And that is the basic idea, but we also want to know how k affects those locations. So we want to know as k increases from 0 to higher numbers, what will happen to the two poles. Okay, so now let's consider, again, create our own little table here again. So we want to know the effect of k on location of the two poles. closed loop has two poles. As you can see, the reason for the two poles is that plus and minus. So the plus minus creates a duality for the two poles. Now, A and C are real numbers. How do we know? Because they represent physical parameters. So cross-section area of a tank or the coefficient of an orifice, they can't be in imaginary numbers. So they're real numbers. So when you take a closer look at this equation for the two poles, is this a real number or an imaginary number? The first part. So A1C2 plus A2C1. Is it a real number? It is a real number. And on top, this is a real and negative number. Okay? So the same here. So this is a real number and a positive number. Definitely a positive number. Now look here. Then you have minus for A1, A2, C1 times C2 plus K. So what you can see is when K is 0, so when K is 0, the two poles are located exactly as the two poles of the open loop. So one of them is located at minus C1 over A1, and the other one is located at minus C2 over A2. So the two poles are exactly located at where the open loop poles are. And it's a good challenge for you to do the math and show it. So set K equal to 0. So K goes to 0. So what is left is 4 A1, A2, C1, C2. Expand this and see that with plus, one term would cancel, with minus, the other one will cancel. So you get minus C1 over A1 for 1, and the second one would be minus C2 over A2. So if K is 0. Now, as K increases, what will happen? As K increases, essentially this will grow in magnitude. Minus 4 A1, A2, C1, C2 plus K, it will grow in magnitude. And eventually, it has the potential of being larger than this. It has the potential of becoming larger than this. So at some point, you will start having a negative number under the square root, which means what? Which means the two poles will start having imaginary parts. So let's see if that really happens. So how can we do that? We can use the root locus command. We can use the root locus command and actually plot the root locus of this system. So let's go and for root locus, let me remind you this. This is a very important point. With the root locus, we always use the open loop transfer function. The root locus command itself calculates the rest of the steps. So what we need to do is to go back to the open loop transfer function, which is right here, C1 over A1S plus C2 A1S plus C1 times A2S plus C2. So let's go ahead and calculate our transfer function. So we'll go to here. And if you have MATLAB open, please use MATLAB. It gives you more information. So CLC. So S is the transfer function variable again. And C1 is 5, C2 is 1, A1 is 1, and A2 is 1. These are the numbers that we decide to use. And our transfer function G is equal to C1 divided by so we have A1 times S plus C1, and that is multiplied by A2 times S plus C2. Okay, so let's look at our locus of G. So please do the same thing in, it would be better to do it in MATLAB because MATLAB gives you a clickable root locus. So I'm repeating the same thing that I did in the online version, in the MATLAB version. So let me give you one of the screens so you can see my MATLAB screen. So A2 is 1, C1 is 5, C2 is 1, and G is C1 divided by A1 times S plus C1 times A2 times S plus C2. So it's 5 over S squared plus 6S plus 5. Then our root locus of G. And the benefit of doing it in MATLAB, the actual software, is that you get a clickable root locus. So you can see as you change value of K, what will happen to the two poles. Now, this is the pole at -1. The other one is the pole at -5. And you have these two poles for what value of K? What value of K will give you these two poles? One at -1 and one at -5. What value of K? Value of K of 0. Because -1 and 5 are the two open loop poles. So if you click on the MATLAB figure, you can see that when your gain is exactly equal to 0, one of the two poles is at -1, and the other pole is at -5. So when the gain is exactly equal to 0. So when K is 0, the two poles of the closed loop are identical to the two poles of the closed loop. Now, as you change the controller gain, both of these poles would move. Then the one that is at -1 and is the dominant pole will start shifting towards the left. And it becomes less and less dominant because at the same time, the pole that is located at -5 would start moving to the right. So at this point, when gain is exactly equal to 0.8, the two poles would be identical. So for people who are watching online, we are talking about increasing as K increases. This pole from -1 moves to -3, and the pole at -5 also moves towards -3. So the pole that is at -1 is the dominant pole, and it becomes less dominant as K increases, and the pole at -5 was non-dominant. So as K increases, that becomes more important, more dominant. And when K is exactly equal to 0.8, according to MATLAB figure, these two are identical and are on top of each other and located at -3. Now what will happen is if you increase K even further. If you increase K even further, each of these two poles will start moving away on a line that is parallel to the imaginary axis. So they move up, one of them moves up, and the other one moves down. So basically you'll start having beyond K of 0.8, you'll start having a pair of complex conjugate poles. So if you want to complete this table based on what we learned from our MATLAB figure, so up to K of 0.8, up to 0.8, you have a pair of real poles. So up to here, you have two real negative poles. So the type of response is exponential rise, exponential decay with no oscillation whatsoever. Now after 0.8, after K goes beyond 0.8, after this, you have a pair of complex, so a pair of complex conjugate. So up to here, the type of response is an exponential rise. As soon as you pass 0.8, you can expect having this type of oscillation. As soon as you pass 8, you can expect seeing some sort of oscillation. Okay, how can we try this? Go back to your Simulink model. Go back to your Simulink model. your Simulink model so far was an open loop Simulink model. So go ahead and close it. And for the benefit of people who are watching this online, I'm going to recreate the Simulink model. So the Simulink model that we have consists of two first order blocks. So the first one is between U and H1, and it's 1 over. So it's 1 over S plus 5, as you recall from the top. This is the relationship between U and H1, which enters the second block diagram of 5 over S plus 1, which is the model of the second tank. And H2 is our output. So what are we going to do? We are going to feed back H2 as our Y and compare it with a negative sign to our R. So not minus plus, and send this to a controller gain K, which in turn then determines what the input to the first tank is going to be. So go ahead and please create this in Simulink. So what you need is to look at the library so you can bring what you need. So what do you need? So you need a summation sign. So I added my summation, but double click on it and make sure the second sign is negative. So it's not, and then you can remove this line, and this time this will turn to being your R. Instead of being U, it's going to be your R. So you're going to bring the summation, connect it here, and then connect this to your H2, which is this line. This is H2. H2 is the output of the second tank. That's H2, and this is H1. So make sure you're feeding back H2, which is the overall output of the system, and not H1. So then you can move this further. Then you need a controller gain. So go ahead and bring a gain. This is a controller gain, and put it right here. And you need to connect the output of the summation to the gain, and output of the gain as input to the tank 1. So this is your controller gain. So if you have anything less than 0.8, like 0.1, our expectation is that we'll have an exponential rise. So let's simulate. Any questions before we simulate? Were you able to follow along? If you have any questions, let me know. I can come to your computer and we can look at it together. But if you simulate, the expected response for both H1 and H2 is still like this. No oscillation. So for example, the first tank takes about still a second, and it gets to 0.02 in steady state. And the second tank still takes 5 times more, and it takes to 0.09, less than 0.1. Can you see that? And we want the second tank's level to get to 1, by the way. When we say R is 1, we want the level of the second tank to get to 1, but it doesn't get quite there. So we need, let's increase K. And remember, when we go back to solving on paper, we want to see the effect of K on a steady state response, and we'll do that calculation as well. So let's go ahead and go up to 0.8. 0.8 still is in the realm of 2 real poles. But look at the response. The first tank shows an interesting phenomenon. See, it goes up and then comes back down. And the second tank goes up without any oscillation, still nowhere close to 1. So it's better than K of 0.1, but we haven't reached 1, which is the desired level of the second tank. So now let's go beyond 0.8. So let's go to 1 for now. And our expectation is that both tanks will now oscillate because the 2 poles are now a pair of complex conjugate. Did we simulate? Okay. So definitely there is some oscillation. It's not as clear in the second tank. So let's keep pushing it up. So let's go to 5 and see if it is easier to see. Now it's easier to see that both tanks oscillate. And do you remember how to get rid of this choppiness? Go to simulation, model configuration parameters, and change your solver from variable time step to fixed time step. And change that fixed time step to a known number, 0.01. So your solver solved the system 100 times per second. So when you re-simulate, you expect to have a more smooth response. So look at this. You're getting closer to 1, but not quite there. Not quite there. So in order to get closer to 1, I need to have a significantly large K value, which will cost us, but let's demonstrate that. So if you go from K of 5 to K of 50, for example, you can expect to get much closer to 1, but much more oscillation too, because as you increase K, the location of 2 poles gets farther and farther from the real axis, which means the damping ratio gets lower and lower. So if you look here, so let me show you, I don't know if K of 50 is here, but see, as K increases, look at the damping ratio. Here on the real axis, damping ratio is 1. But as you increase K, see, damping ratio goes down and overshoot percentage goes up. So there is a trade-off here. As you increase K, I'm going to write this down. So as you increase K, as K goes up, the system becomes faster. Oscillation starts happening. After 0.8, after 0.8, basically damping ratio goes down as K goes up, and error steady state also goes down. And I'm going to show you what the transfer function between error steady state and R, and show the effect of K on it. So this is, by the way, this is E, the error. So I'm going to challenge you to finding in the transfer function between error as output and R as input. I'll give you a minute to calculate that transfer function. And that way we should be able to see the effect of K on steady state error. So go ahead and calculate E over R, please. So the transfer function will have a numerator and a denominator. So we know the rule is, in the numerator sits what is between the input and the output. Input here is R, output is E. Is there any block between the two? There is none. So it means 1 goes in the numerator. Now in the denominator, because it's a negative feedback, it always starts with 1 plus. And after plus, whenever you have a closed loop configuration, after the plus comes the content of the loop, no matter which transfer function you're trying to find from this. So the content of the loop is K. I'm going to use the numerical values. So K times 1 over S plus 5 times 5 over S plus 1. So if you make s plus 5 times s plus 1 the common denominator, this becomes s plus 5 times s plus 1 here. And in the denominator, we'll have s plus 5 times s plus 1 plus 5 times k. So I'll give you a second to find any mistake that I might have, and let's correct it before go any further. Any mistakes? So if we agree that this is the transfer function between r and e, then you can answer this question. If r is 1, so if r is 1 means you want the level of the second tank to get to 1 and stay at 1. That's the meaning of r being 1. Look at the feedback loop. So when you say r is 1, you're saying I want h2 to get to 1 and stay at 1. That's what you're saying by choosing r to be 1. So if r is 1, it means r of s is what? What is r of s? It is 1 over s. So you can find error steady state from this transfer function by using final value theorem. So error steady state is equal to s times e of s when s goes to 0. That's the theorem in limit s times e of s when s goes to 0. So s comes from the theorem. And for finding e of s, we will multiply r of s by the ratio of e of s over r of s. Okay, s again gets repeated. R of s is 1 over s, and this is the transfer function that we just found. So that's what is the transfer function? The transfer function is s plus 5 times s plus 1 in the numerator. In the denominator, we have s plus 5 times s plus 1 plus 5 times k. And in all of that, we let s go to 0. So error steady state, therefore, is equal to, from the numerator, we get 5. And from the denominator, we get 5 plus 5k. That is error steady state for a unit step input. So when k is 1, error steady state is equal to what? Error steady state is equal to 1/2. Go to the simulation and see if the simulation would support that. So if k is 1, run the simulation and see if the level of the second tank stabilizes at 1/2, which is equivalent to having 1/2 error. Does it? So look at the response of your system with k of 1. So error steady state 1/2 means y steady state. So error steady state, by the way, is equal to r minus y steady state. So r is 1. So that means y steady state is 1/2. And if you look at your simulation, you can see that y steady state is 1/2. So yellow is y steady state, which is a level of the second tank. And you can verify that. If k is, what is another easy number to calculate? If k is 2, for example, so if k is 2, that is 10 plus 5, 15, 5 over 15, 1/3. So for k of 2, steady state error is 1/3. So try that. Simulate. And see where it settles. So 1/3 means 0.33 is the error. So that means 0.66 is the steady state value of H2. And you can see it basically gets there. So we found steady state error. You can also find Y steady state. You can also, by the way, find H1 steady state. You can find H1 steady state from the same thing. So I'm going to again challenge you to find a transfer function between R and H1. So I'm going to ask you to find a transfer function between H1s as the output and R of S as input from the exact same block diagram that I have up here. So find H1 as output. Let me switch screens so you can see better. So find H1 as output, R as input. What is the transfer function between R and H1? Again, you need to apply the exact same rule. This time I'm going to wait on you. So if you have the answer, raise your hand and give it to me. Otherwise, I'll wait until you get to the answer. You got it? Okay, tell me. Of course. Enough or further? You got it? The transfer function? Yeah. Tell me how you find it, and then so what goes in the numerator? So let me bring the block diagram. What goes in the numerator?
K times 1 over S plus 5.
And the logic is these are the two blocks sitting between R and H1. R as input. Okay, so let me put that down. So it in the numerator goes K times what?
1 over S plus 5.
1 S plus 5. How about the denominator?
Just 1 plus and then the same thing.
The same thing as 1 over S plus 5, or there is more?
Actually, there is more.
What is the next one?
Times 5 over S plus 1.
Exactly. So this is the transfer function. And you can simplify this. So if you make s plus 5 times s plus 1 the common denominator here, so s plus 5 times s plus 1 here, you will have s plus 5 times s plus 1 plus 5k, and in the numerator you still have s plus 5 and k in the numerator. So if you further simplify this, you will have k times s plus 1 in the numerator, and in the denominator you have s plus 5 times s plus 1 plus 5k. What is this? This is h1 over r as the transfer function. So what is the benefit? You can, for example, when r is 1, which means r of s again is 1 over s, you can calculate h1 steady state. So h1 steady state. So you can calculate h1 steady state from final value theorem. And according to the theorem, this is equal to s times h1 of s when s goes to 0. And the way you find this is by finding r of s and multiplying r of s by the transfer function between h1 as output and r of s as input. So let's go ahead and calculate for r of s of 1 over s. So again, h1 steady state becomes s times r of s, which is 1 over s, times the transfer function, which we just found, k times s plus 1 over s plus 5 times s plus 1 plus 5k, when s goes to 0. So s in the numerator and the denominator of the first fraction they go away. So what is left is k, and from the denominator you have 5 plus 5 times k. So for example, when k is 1, h1 steady state is going to be 1/10. And you can go back to your simulation, to your Simulink, and set k equals 1 and run the simulation and look where the blue curve settles. Does the blue curve settle at 0.1? So that tells us we've done this correctly. If k is 2, for example, it would be 2 over 15. So if k is 2, h1 would settle as roughly 1/7, which is roughly 1.134. So you can see that our simulation and our calculation, they support each other. If you think the fun is over, think again. We are going to now use the state space model. State space model of the system, and try to stay in state space and do the calculation for closed loop A matrix. So go ahead, please, and find the A matrix from the two differential equations that we have in the top. So we need the A matrix, and then we'll use the A matrix to calculate. Of course, we also need B and C matrices, because in calculating the closed loop A, we need those two matrices. So let me remind you, if we have the A matrix of open loop and B and C matrix of open loop, we can find closed loop A matrix. So our goal is to do this, to find the A matrix of closed loop with a proportional control. So the first step is to find the A matrix. So if you recall, the first differential equation is this. It is h1 dot is equal to 1 over a1 u minus C1 H1, that's H1 dot. H2 dot is 1 over A2 C1 H1 minus C2 H2. So that's the exact differential equation that we had from the past, just rewritten so it would be easier to convert it into a state space model. Now, the X matrix, the X vector, the state vector for this system is made of H1 and H2. These are the two variables that are being differentiated if you look at the two first order differential equation. So that's our state vector. Our output is H2. We're really interested in knowing the level of the second tank. And our input is the flow coming to the first tank U. So I'll give you a minute to calculate A, B, C matrices. So, and again, I'll wait until you tell me you have the answer, and then we'll work it out on the board. So find the four matrices A, B, C, and D, which are essential for the first order, the open loop system, as the model of the open loop system. Okay, again, we're looking for A, B, C, and D, the four matrices. Let me know if you have it, and I'll follow along with you. Ready? Still working, or you got it and want to give it a shot? Do you have it?
Yeah.
What is it? So the A matrix.
So A matrix is negative C over A1.
So negative C, which C?
Negative C1.
So negative C1 over A1 gets multiplied by H1, and then what is next?
0.
Okay, so nothing gets multiplied by H2 for H second row.
C1 over A2.
Uh-huh.
And then negative C2 over A2.
Mm-hmm. So and this comes from the second differential equation. How about B?
1 over A1.
Where is it?
The top.
Okay, 1 over A1 gets multiplied. How about here?
0.
Nothing gets multiplied, yeah? And how about C? What did you put for C?
0, 1.
0, 1, because?
Because 0, well,
0 gets multiplied.
H2.
Mm-hmm.
And then so we have to multiply 0 by H1, cancel that out, and then 1 by H2 to get H2.
Yeah, I think this is correct. Did you all get the same thing, or do you at least agree? Okay, very good. So this is open loop. So this is no control yet. So open loop. Now, if you want to do the same thing as we did before, so if our system is here, so system, where U enters as the input to the first tank and Y comes out as H2, then we are trying to do the exact same thing. The difference is the system doesn't necessarily and directly, readily distinguishes between H1 and H2. So R here, minus Y here, error here. So exact same thing, but the state space model captures the whole thing. It doesn't separate it into two first order transfer functions as we had before. So the next step in designing is to calculate a closed loop. A closed loop, as you know, is equal to A minus K times B times C. So we need to calculate B times C first. So B times C. So B is 2 by 1, C is 1 by 2, so the result would be 2 by 2. So it's a 2 by 2 matrix. So the first row, first column is 0. First row, second column is 1 over A1. Row 2, column 1, and row 2, column 2 are both equal to 0. So if you multiply this by K, so K times B times C simply is the same thing, except here we have K over A1. So that's K times B times C. Okay, so now let's go ahead and subtract this from A, which is at the top. So it would be so 0 gets subtracted from minus C over A1, so it remains at minus C1 over A1. In still row 1, K over A1 gets subtracted from 0, so this becomes minus K over A1. Now we are up to row 2. C1 over A2 gets subtracted by 0, so C1 over A2. And minus C2 over A2 again gets subtracted by 0, so it remains the same. So that's A of closed loop. Now in order to know the eigenvalues of the closed loop, we are going to set the determinant of lambda I minus a closed loop equal to 0. That's the method for finding eigenvalues of any system, including this system, which is the closed loop system. So let's go ahead and find the determinant. So lambda I is lambda 0, 0, lambda, and we are subtracting from this minus C1 over A1 minus K over A1, C1 over A2 minus C2 over A2. This is the determinant. So this determinant becomes lambda gets subtracted by minus C1 over A1, so it becomes lambda plus C lambda plus C1 over A1. 0 minus minus, so it becomes K over A1 with positive. 0 minus, so it's minus C1 over A2. And lambda minus minus becomes lambda plus C2 over A2. This is the determinant. So let's go ahead and find the determinant. So the determinant would be lambda plus C1 over A1 times lambda plus C2 over A2 minus minus becomes plus C1K over A1 A2 equals 0. Okay, so let's call this equation 2 a polynomial from which you can find eigenvalues of a closed loop. Let's go back to what we did. I'll scroll back. Don't worry if you have if you need more time to write it. Let's go back to our closed loop transfer function. The closed loop transfer function that we found was here. So the closed loop transfer function was there, and the polynomial that we found for finding the poles is this equation 1. So if you compare equation 1, to the second equation, let's see the difference. The difference is just in appearance. So if you take this equation and multiply it by A1, A2, it becomes like this. So it becomes, if you multiply this by A1, A2, it becomes so if we multiply A1, so it becomes A1, A2 multiplied by lambda plus C1 over A1 times lambda plus C2 over A2 plus C1K still equals 0. So the result becomes, so if you multiply A1 by this and A2 by this, the result becomes lambda A1 plus C1 times lambda A2 plus C2 plus C1K equals 0. Let's go back and compare it one more time to equation 1. Do you see any similarity? They're identical equations, except that one, the variable is s, and the other one is lambda. So the poles of the transfer function that we got from the previous calculation are exactly the same as eigenvalues of the A closed loop that we got in this calculation. So everything that we said about the behavior of the system or the way that the poles change is equally applicable to the eigenvalues of the closed loop system. Okay, I am going to stop here. Thank you.